Our first speaker is Mulligan, who's a research scientist in CCB and going to tell us about Rosetta and biomolecular modeling. So take it away.
Okay. Hi, everyone. Can everyone hear me? Good. As the chair said, I'm Vikram Mulligan. I'm part of the biomolecular design group. We used to be called the systems biology group, and we decided to change the name to better reflect what we actually do. I want to start by just giving a little disclaimer here. This is me in grad school. You'll notice lab coats, bottles of guanidinium hydrochloride and other things, apparatus. I'm trained as an experimentalist, not as a software engineer. And this means a couple things. One is, for me, the software engineering is a means to an end. I need the tools, the software tools that I want to use to get a scientific result. And for another, it's given me a lot of appreciation for the struggles of someone who might be formally trained in experimental methods and in science, who has to write software methods in order to do what they want to do. And so one of the challenges is, how do we engineer our software? How do we architect our software so that it's accessible to a biologist who doesn't just want to use it, but also who wants to modify it? In this talk, I'm going to spend about the first third of the talk just talking about the science we do, no software engineering, just to motivate the rest of the talk. And then I'll tell you about the current tools we use, Rosetta, and how we've extended them over the years. And then about a new project that I've been working on called Masala, which is intended to be a successor to Rosetta that addresses some of the problems that we have with it. And I've got one slide at the end about whether there might be certain problems that we're solving for biomolecular modeling that are general problems in scientific software engineering that we might be able to carry over to other projects. So diving into the science, as I said, our group is now called Biomolecular Design. In general, we're interested in understanding the theory of how proteins and other heteropolymers fold. Now, there are all sorts of applications of this. The one that jumps to everyone's mind is predicting structures. And that's somewhat interesting to us. But even more interesting to us is designing new things that fold in new ways. The ultimate test of whether you really understand something is whether you can apply those principles to something you've never seen before. And so we're interested in making things that fold that are not necessarily made of natural amino acids, that could be made from exotic chemical building blocks. If we can do that well, there are all sorts of practical things we can do, like design drugs, design enzymes, make new materials, and these can have useful impacts in our society. Now, in addition to this, we're interested in developing algorithms for these purposes, including algorithms for quantum computers, not just for classical computers, and engineering all of this into a pipeline for doing something robustly, not just a magic show for doing something once and saying we did something. Doug Renfrew is another research scientist in the group. He and I together are now heading the group. And he's been here at Flatiron a lot longer than I have. He has worked on structure prediction and functional annotation to try to understand what all the proteins in the microbial universe are doing. Doug and I have both worked on designing peptides to fold that are made not just of natural amino acids, but also exotic chemical building blocks like these chemical cross-linkers or D-amino acids to get helices of opposite-handedness to pack against one another. And these are all experimentally determined structures, I should mention, of molecules that we designed, and then we went and made and solved structures experimentally. Now, these ones just fold. They don't do anything. We've made some exotic foldamers, ones that use symmetry in order to bind a metal. So this was a metal binding peptide that I designed that has S4 symmetry, which involves mirror operations. This is something you cannot do with canonical amino acids because they all have the same handedness. But if you use a mix of left and right-handed amino acids, you can. I designed a bunch of these, and we decided that because this is a hard molecule to synthesize, we'd synthesize one. And we synthesized it, and we solved the X-ray crystal structure, and we successfully designed the thing to sub-angstrom precision. I'm not showing all the side chains here that cause it to fold, but This is just showing that we can get something to fold and function a little bit too. So this is a metal binding peptide. In addition to peptides, Doug has done a lot of work on peptoids, which are similar to peptides, but the side chain comes off a different atom. And you might say this is a small change, but it actually has huge impact on the folding properties and also on the chemical synthesizability of the molecule. Chemists love peptoids because they're easy to synthesize, but people in the folding field might not like them so much because it's all the secondary structures that you can make with peptoids go out the window. And so we have to come up with clever methods to figure out what these things can fold into. Now, we're interested in these things, and in particular, we're interested in chains of peptides or peptoids that connect back on themselves and form rings. And the reason we're interested in those is because we can structure them rigidly, and because they're possibly a very interesting new class of drugs. So most of our drugs are small molecules. You know, this is acetaminophen, Benadryl, penicillin, and darunavir is a relatively large small molecule used to treat HIV. Small molecules are great because they're easy to synthesize, they're shelf stable, they cross biological barriers, they get into cells, they get across your gut-blood membrane, they're orally bioavailable, but they're not so great because they're often not very specific. Anything that and a small molecule is like a small luggage key. If it fits into one lock, it fits into a bunch of others. So it's going to bind to things other than its target and produce side effects. At the other end of the scale, we have large molecules, proteins. A lot of the protein drugs that we have are antibodies that very specifically recognize one thing, presenting a huge surface area for recognition, although some of them are enzymes as well. And these are great for specificity, but they're bad for administration. It's hard to produce a lot of protein, they're not very shelf stable, they don't get across biological barriers, and we've got an immune system that has evolved to recognize foreign proteins and degrade them. In between the two in size are peptides and peptide macrocycles and peptide-like molecules. And here are the relative scales of all these molecules. And these kind of combine the advantages of both classes. They are more bioavailable and better at getting across barriers than the proteins are, but they present larger surface areas for specifically recognizing their targets than the small molecules do. The trouble is we've only got about 20 peptide macrocycles and a handful of additional macrocycle-like things in the approved drugs, and most of those are just things that were found in nature. We haven't until recently had good ways of designing these things. Now there is one problem with things in this medium-sized range. So a small molecule, if you try and get it to bind to your target, so let's say this green thing is your target protein, and this red thing is a small molecule. And it binds into a little pocket in your target. I already said that the problem is that it'll probably bind to pockets in a bunch of other proteins as well and produce side effects. So you make the molecule larger and you try and make more specific interactions with your target. The trouble is a larger molecule in this medium-sized range is floppy. And if it's flexible in solution and ordered in the bound state, there's an entropic penalty associated with binding. And that pulls the equilibrium towards the unbound state. So you've made the molecule bigger, but now it doesn't bind as well. And in addition, if it can flop around, maybe it can flop around into an alternative conformation and bind to something else. So it might not be any more specific either. The solution is make the molecule rigid in the binding competent conformation for your target. Then it can't flop around into a different conformation and bind to something else. And it also doesn't have this entropy problem, which means that the interaction with the target can be driven by favorable enthalpic interactions, and you can get nice high affinity binding. So that's the theory. We wanted to try it out, see if we can actually design things that rigidly fold into their binding competent conformations and bind to a target. A couple years ago, we published this in PNAS, computational design of a panel of peptide macrocycle inhibitors of NDM1, New Delhi metallo-beta-lactamase, which is an antibiotic resistance factor. The idea is if we can inhibit the thing that breaks down antibiotics, maybe we could make all the old antibiotics useful again by co-administering the inhibitor with the old antibiotics. So we designed peptides to do this. Here in light colors, I'm showing the design that came out of the computer, and in dark colors, I'm showing the X-ray crystal structure that came from experiments. So these peptides fold into the structures we designed with, again, sub-angstrom precision. And they also bind to the target. Here's the design, here's the experiment, and they bind in the design binding mode. And they had reasonable affinities. They weren't quite as high as we'd like. But the significant thing is, you know, I made 1,000 designs of the computer. I picked 7 to synthesize, and all 7 inhibited. And 6 of them inhibited better than the lead small molecule that we had. In a typical drug discovery pipeline, you screen 100,000 compounds to try to find one that inhibits. So the whole point is to reduce the number of experiments that you need to do. More recently, during the pandemic, everyone in the world turned to trying to target SARS-CoV-2. SARS-CoV-2, of course, has this spike glycoprotein that is involved in allowing the virus to enter host cells. It exists in a closed state and an open state, and only in the open state can it interact with ACE2, the human protein that it uses as its receptor to get into host cells. So if you can pull the equilibrium towards the closed state, you might be able to neutralize the virus. And so that's what we wanted to do, design molecules that would specifically bind the closed state, stabilize it, and pull the equilibrium towards the closed state. The analogy I use is the sandworm is only dangerous if the mouth is open. So we want to make something that'll close the mouth. So we made some molecules like this, designed them computationally, synthesized 20 of them. And of these 20, the top one did inhibit in vitro pseudovirus neutralization assays, did inhibit the virus. It wasn't a great inhibitor, though. It was a little bit weak. So our methods could be better. The other problem was this was designed for the Wuhan variant. So this pink thing is the peptide. It's actually 3 peptides linked by a 3-fold symmetric linker, which gives you a molecule with the same symmetry as the target that we're trying to inhibit. Now, the virus, of course, evolved, and we had the Delta and then the Omicron variants. The nice thing about a peptide, unlike a small molecule, a peptide is mutable. You can introduce amino acid substitutions, and so we decided, okay, well, can we actually show this to be an advantage? Can we redesign our best Wuhan binder in order to bind the Omicron variant? And so I did that. I took the structure. Again, this is the computer model. We don't have a crystal structure of this yet. Of the best binder bound to the Wuhan variant, identified the sites of mutation that I'd have to change in the target in order to get the Omicron variant, modeled in the target mutations, and then started exploring conformation and sequence space to try to find good amino acid sequences that could make favorable interactions with the Omicron variant. We have some plausible designs now. These are currently being synthesized, and we have a collaborator at the FDA who's very interested in these and who's going to be testing them out shortly, as long as the government doesn't shut down. So that's a work in progress. The other thing, and this is before we move on to the actual software engineering, this is the last thing I'll tell you about. The other thing is trying to make peptides permeable. Most peptides, if you just design a random sequence, that sequence will not get across a cell membrane. However, we know that peptides can get across cell membranes because there are natural peptides that do. Cyclosporin is a good example. So we want to design peptides to do this. And we had a recent paper in Cell where we successfully did this. These are peptides modified with N-methylation at some of the key residues. And these very readily penetrate cells. And these are PAMP assays and Keiko2 permeability assays. And we were able to get peptides that permeate cells as readily as any small molecule. Now, the caveat here is these are peptides that are not drugs. They only get into cells, but once they get into the cell, they don't do anything. The next challenge is, can we make a peptide that gets across a membrane and binds to its target? And we haven't done that yet. We're trying. So I think that gives you an idea of what we're trying to do scientifically, what we're interested in, what our goals are. We have to rely on software to do all of this. And the experiments are very, very hard. The total chemical space is far, far vaster than anything we can screen experimentally. So we want to make good computational predictions so that we can do the number of experiments that we can do and actually get a hit in that number. And so we've got challenges here. One is accuracy. If we can make our methods more accurate, then we have to screen fewer designs in order to find a hit. If we had a success rate of 1 in 10, then we have to screen 10 designs. But if we have a success rate in 1 in 1,000, we have to screen 1,000 designs. And I should say also that we want to be able to design enzymes, which is something we're really bad at. There are a few examples of computational design of enzymes. They've never made a good enzyme. So we want to get better at that. Generality and extensibility. We want our methods to work not just with canonical amino acids, but with building blocks we've never seen before. We want to design enzymes that operate on substrates that we've never seen before. And so we want nice general methods, and we want to be able to extend our methods as people come up with better scientific ideas. And we want it to be easy for biologists and chemists to extend our methods. And then trackability and efficiency. We want to be able to do these calculations in the amount of computing power we have. We'd like to reduce the amount of computing power necessary, if at all possible. And in some cases, we have combinatorial problems that are fundamentally intractable to do exhaustively. And so we come up with clever heuristics to make those somewhat tractable for some sizes of problems. However, we need new clever ways to get beyond the current upper limits of sizes of problems that we can possibly do, even with all of the computational resources on Earth. So what are we using right now? Well, we're using Rosetta. Rosetta is a set of C++ libraries and applications that has been developed over the last about 25 years now. It's initially been designed for first protein structure prediction and then protein design. For a lot of its history, Rosetta was very, very hard-coded to only work with the 20 natural amino acids. More recently, we've generalized it to work with more exotic building blocks and to try to turn it into a general heteropolymer modeling suite. The software is not open source, I should mention that. It is free for nonprofits, academics, and governments, but we license it for a fee to commercial users. And that fee pays for the Rosetta conference and a few other things. So what does it do? Broadly speaking, Rosetta keeps track of atoms and bonds and their kinematics. And by kinematics, I mean, if you start rotating around one bond, what moves? If you have a chain of atoms? And then built on top of that are all sorts of algorithms for sampling conformations and or sequences, or both together. And then algorithms for computing scores, usually energies. And these are just based on force fields for the most part. And then built on top of all of that are more complicated protocols for doing particular things you might want to do. Docking molecules together to predict Dock conformations, designing sequences to achieve some sort of function, predicting structures. And these string together all sorts of different modules that are doing these more atomistic things. In a sense, I mean atomistic, not in the chemical sense, but in the procedural sense. One thing to note is a composite protocol will often be fairly heterogeneous. You'll do task A for a few seconds, and then task B for a few seconds, and then task C for a few seconds. So it's not like molecular dynamics simulations where you might run exactly the same type of task for days. Now, that being said, that is something common to a lot of scientific software, I think. Even if you're doing one type of simulation, you might have a long simulation phase, but then a series of analysis phases where you analyze the results of your simulation. Rosetta started out in the late 90s as Fortran code. And it was very, very specific Fortran subroutines for doing specific things. So at the command line, you would sit down and say, okay, today, what I want to do is optimize rotamers of this particular structure. And you'd enter your command line inputs and you'd get your outputs. And then you'd say, okay, I'm going to take some of the outputs and I'm going to enter new command line inputs to relax these structures or something like that. And it was a very manual process that prevented the emergence of much larger composite protocols. In the early 2000s, Rosetta 2 was developed. It was an automatic conversion of the C++ code to Fortran. Don't do this. It's bad. You basically end up with Fortran with C syntax. And that's not a good thing. And so in around 2010 or so, there was a massive effort to rewrite Rosetta from scratch in modern object-oriented C++. And this created a much more usable and versatile and modular set of programs. In 2011, two scripting languages were introduced, PyRosetta and Rosetta Scripts. Rosetta Scripts is an XML-style scripting language that lets you just chain together different modules in Rosetta. PyRosetta is a little more advanced. It gives you full program flow. Rosetta 3 also introduced MPI-based job distributors so that you can do things on a massively parallel scale, although it's almost embarrassing parallelism. Typically, you're doing independent samples in either a conformational sampling trajectory or a sequence sampling trajectory in parallel. But Rosetta 3 has almost no shared memory parallelism. I put in a little bit more recently, and no support for GPUs. And some of the reason for the lack of GPU support is the heterogeneity of the tasks that we might do in any given protocol. And as I said, more recently, Doug and Andy Watkins and a bunch of others and I have worked to generalize Rosetta 3 so that it's not just a protein modeling package, but a general heteropolymer modeling package. Here's an example of a Rosetta workflow. This is kind of the process that I used to design those NDM1 inhibitors that I told you about earlier. We start with the experimentally determined structure of a target protein that we want to bind to. We dock in an initial stub, and then we build out a chain of amino acids and sample conformations of a macrocycle in a binding pocket on the target. And then for each plausible conformation that we sample, we use fixed backbone rotamer optimization algorithms that I'll tell you about in a moment to design a sequence. Then we make thousands of designs, and we try and throw away as many of them as possible using whatever metrics we can compute that are cheap and easy to compute. And whatever passes our low-cost filtering, we carry forward to high-cost simulations. Now we fix the sequence, and we start saying, all right, we've got a candidate sequence. Does this actually have the properties that I want it to have? Does it actually rigidly fold into the binding competent conformation? And this allows us to rank the remaining designs, and we pick the top ones for synthesis and experimental evaluation. And you can see as you're going through this process, you're going from many candidates to few candidates, and you're going from very little computational expense per candidate to very high computational expense per candidate. In this particular case, the first three steps here have been implemented and can be implemented as Rosetta Scripts XML and can be executed in parallel using the Rosetta Scripts MPI application. This validation step is a separate application that's also MPI parallelized that I wrote. And I'll tell you a little more about these steps. So the first three steps, again, docking a stub into the target protein, growing out a chain of amino acids, converting to a vector representation so we can use kinematic closure algorithms to try to solve for closed conformations of the macrocycle. And this allows us to very rapidly sample macrocycle backbones. We can sample, I'd say on the order of tens of thousands per second this way. And then for each plausible backbone that we sample, we design sequences. And all of this, as I said, is done in Rosetta Scripts. In Rosetta Scripts, we have objects called movers that take a structure as input. We call structures poses. Take a pose as input, do something to it, and produce a pose as output. So we just chain together a docking mover, an extension mover, a kinematic closure mover, and a design mover. One thing Rosetta does pretty well, but which we could do better, is this rotamer optimization problem. This is an NP-hard problem. The problem is, given a fixed backbone, so we've already sampled backbone conformations, and given side chains that come off that backbone, where we don't yet know the side chain identity or the conformation of the side chain, choose a side chain identity and conformation at each position, which we collectively call a rotamer at each position, such that an objective function is minimized. We make a list of candidate rotamers at each position. These can allow both the sidechain identity and its conformation to vary. We write down an objective function, usually an energy function. And to make this efficient, we use pairwise decomposable energy functions. So energy functions that can be expressed as a sum of terms that are either dependent on a single rotamer at a time or a pair of interacting rotamers at a time. And we pre-compute internal rotamer energies. This is an ON calculation if you've got a total of n rotamers in your problem. And we pre-compute pairwise rotamer interaction energies. This is an ON squared calculation. So far, everything's polynomial time. It's all tractable. The thing that's not polynomial is the exponentially scaling combinatorial space of all the possible selections of rotamers that you could possibly choose. So we can't do this exhaustively, which means we fall back on the old tried and true Monte Carlo. In this case, we're using Monte Carlo not to generate physical distributions of states, but just as a convenient means of optimizing, of sampling the space and finding a fairly low energy solution. This is not guaranteed to converge to the global optimum, but as long as it converges to something near the global optimum, we're happy. And our moves are basically just start with a random selection of rotamers, substitute one rotamer for another at a position, update the energy based on your pre-computed one-body and two-body energies. If the energy goes down, accept the move. If it goes up, accept or reject it with conditional probability dependent on the amount by which it's gone up. And if we do a few million moves like this, which we can do because everything's pre-computed and we're not working with molecular geometry at each step, we end up getting a pretty good solution out. And then we just map those rotamers onto the backbone. One problem with the way Rosetta does this is everything is kind of rigidly written. The only option you have in Rosetta for solving this problem is Monte Carlo. It doesn't give you an option to try it a different way. And mathematicians have come up with all sorts of clever ways of solving this problem. This is actually a general mathematical problem called a cost function network optimization problem, not specifically a rotamer optimization problem, which is the other problem in Rosetta. In Rosetta, we have a rotamer optimizer that operates on rotamers. So if you have another problem where you want to do cost function network optimization that has the same functional form, you actually can't use the Rosetta machinery to solve it, or it's a pain in the neck to use the Rosetta machinery to solve it. You have to trick Rosetta into thinking that it's operating on rotamers. The validation application that I told you about, this is at the end of the pipeline. So we've got a bunch of candidate peptides that we've designed. We have sequences for all of them. And we want to ask the question, of these sequences, which ones rigidly fold into the designed conformation and which ones are flexible? So we take each sequence, we fix the sequence, we take the peptide and put it into all sorts of alternative conformations. And that's what all these points are. On the horizontal axis here, I'm showing the RMSD to the design conformation. How much does each point deviate from the design conformation? And on the vertical axis, I'm showing energy. So we create all these conformations, we relax them all, we pack the rotamers on all of them, but we don't change the sidechain identities. And what we want to see is something like this, where there's a unique low energy state very close to the design conformation, and everything else is high energy. And there are metrics we can write down that help us quantify this. This is one that varies from 0 to 1, depending on how funnel-like this landscape is. I put a lot of work into making this efficient, especially on the older Blue Gene machines, which are now gone. We use a hierarchical MPI job distribution system where we have one director node that farms out jobs to a whole bunch of managers, which then farm out jobs to a whole bunch of workers. The workers do the sampling, and we have analysis and data reduction up the hierarchy as the workers transmit their results up. Because we have this hierarchical structure and we can have as many managers in the middle layer as we want, and in fact, we can have as many layers of managers as we want, we get almost linear performance scaling up to tens of thousands of cores on massively sized supercomputers. This was fairly successful. I told you that we synthesized 7 peptides out of the thousands we designed. One thing that was really nice about this is the predictions that came out of the structure prediction application, the conformational sampling application for how rigidly folded these peptides were, corresponded very well to the experimentally observed inhibition. So this is inhibition here. This inhibits more. This inhibits less. This is computational prediction here. This is more rigidly folded. This is less rigidly folded. So the most rigidly folded thing was the thing that inhibited the most. So this kind of confirmed our working hypothesis that pre-ordering peptides and their binding competent conformation is one of the keys to getting good inhibition. And what is really nice is we actually predict the rank order of these 7 peptides. So this is great. We've got a tool that predicts for us which peptides are worth going into the wet lab and synthesizing. Not everything is great, though. Intuitively, not only should a peptide's inhibition depend on how rigidly folded it is in the binding competent conformation, it should also depend on how well it interacts with its target, how good the interactions are. Now, all of these peptides were optimized for favorable interactions with the target, which meant that among these 7, we did not have the precision to discriminate between them. So if we predict now interaction affinity with the target versus inhibition, we see no correlation at all. And this gets back to the problem of precision and accuracy and whether we could make this better. Precision and accuracy are one of the things that inhibit our ability to design enzymes. And now I'm talking about an aspirational goal, which is designing enzymes. In the past, this is how enzymes have been designed. First, you identify the transition state of the reaction you want to catalyze. Then you design a protein that wraps around the transition state, that stabilizes the transition state to try to accelerate that reaction. This works. You do get enzymes out. However, the enzymes that have been designed in the past this way have been really poor enzymes. And in order to turn them into good enzymes, we had to do directed evolution. Now, why does this not work very well? And I should mention also that this is very, very laborious, and it's only worked about 4 times. There are about 4 examples in the literature of designed enzymes. So it's not something that's reproducible and which works consistently. So why is it hard? Well, part of the problem is we're using too simple a picture of what an enzyme is. An enzyme, they tell you in the textbooks, is something that lowers the activation barrier to catalyzing a reaction. Takes the transition state, lowers its energy. And you get these nice one-dimensional reaction coordinates where you're going from substrate to product with a high energy state in between, and you're lowering the energy. The reality is reaction coordinates are multidimensional things. There are all sorts of ways that you can go from substrate to product in the multidimensional landscape. There are all sorts of energies with all of those intermediate configurations. And there's an entropic consideration as well. There are all sorts of off-pathway motions that you could have that do not lead to product. An enzyme is something which not only reduces, oh no, there we go, which not only reduces the energy of the transition state, but also prevents you from going off this path and destabilizes all the alternative states. And one of the analogies I use is a stapler is an enzyme. If you took a washing machine and you put a bunch of staplers and a bunch of paper clips and a bunch of pieces of paper in your washing machine and you tumbled it for a week, at the end of that week, you would find a few pieces of paper got stapled together just by chance. Just sometimes the stapler swung open and closed on a staple and closed on a piece of paper, and you would have some pieces of paper stapled together. Do the same experiment without the stapler, and you wouldn't get any pieces of paper stapled together. So the stapler has accelerated this process. Now, if you take your stapler, which has 1 degree of freedom of motion, and replace the hinge with a ball joint and do the experiment again, you're going to get far fewer pieces of paper stapled together. So the enzyme, the stapler, is not only lowering the activation barrier to getting through that transition state, but preventing non-productive motions. And this is something we do not consider in our computational design pipeline, and we're starting to think about this. So in order to make this better, we need a way of getting away from the static view of proteins as rigid things to a more dynamic view of proteins as things that can move. And this is a simulation I did with a protocol I developed in Rosetta to just identify major degrees of freedom of motion of a protein. You can do this with MD simulations as well, but you can do it much, much faster in Rosetta. This was seconds in Rosetta, and it would have been days in MD. This involves a set of modules I developed called ensemble metrics, which get away from this notion that we're going to work on one static state at a time. So we're still going to sample one static state at a time, but ensemble metrics allow you to have one state going through your pipeline at a time, and then they have an observation stage where each state that goes through can be viewed by this metric, and the metric can record whatever it wants to from this. And after it's viewed a whole bunch of states, it's allowed to produce at the very end a report where it does whatever analysis it wants to on the data it's collected. This works well with our MPI job distributor as well. So when we have many parallel processes, so here are two worker processes and one master process, each worker process is generating a whole bunch of samples, and the ensemble metric exists in each worker process, observing all the samples. And at the end, all the worker ensemble metrics send data to the master ensemble metric for it to produce its report. So you can, in massively parallel, sample millions of conformations without ever storing them all on one node. So this is one thing we're trying to do, trying to design for dynamic motion, which means first understanding dynamic motion. How we incorporate this into a design process, we're not quite sure. The other thing we're trying to do is get away from force fields. Proteins are not balls and sticks. They are nuclei surrounded by a cloud of electrons. And this is the output of a QM calculation done on a protein molecule. Now, one question is, how do you do a QM calculation on something the size of a protein? Proteins are thousands of atoms. And it turns out that this is not a problem we had to solve, because people in the quantum chemistry world have thought very hard about this problem and have come up with good solutions. It's just that we're not really using them in the biomolecular modeling world. So this calculation was done with fragment molecular orbital methods, which divide a large problem into smaller pieces, do QM calculations on the pieces, and put together the solution. It was also done with DFTB, which is a semi-empirical method that is much faster than the more rigorous methods that you might use instead. And there's going to be a trade-off between rigor and speed, and that's fine. But we want to use this in a Rosetta pipeline. And so one thing that I've worked on with Ben Brown at Vanderbilt is just getting Rosetta to talk to quantum chemistry software. So in the middle of a Rosetta protocol, we can just do a QM calculation and then take the result and continue on in the protocol. And this has opened up all sorts of new things that we can do. Now, there's always the trade-off between speed and accuracy. We don't want to use quantum chemistry for every single energy calculation that we can do, but we can use it alongside our force fields, where we might do lots of force field optimization and then a quantum chemistry calculation in the middle to decide whether to continue, and then lots more force field optimization. And these are just the classes we've implemented in Rosetta. We can basically calculate energies, but we can also do geometry optimization using quantum chemistry. And so now we're experimenting with all the things that this opens up. Now, I've got 20 minutes left, and in the last little bit, I'm going to tell you about the limitations of Rosetta and how this is motivating new software called Masala. And we've seen some of these limitations here. So generally, limitations affect accuracy, tractability and efficiency, or generality and extensibility. So the first limitation here is we've got lots of new hardware available to us, like GPUs, that our software was never written to take advantage of. We saw a talk yesterday about how you can engineer new software to take advantage of GPUs, but the reality in scientific software engineering is often we've got 25-year-old software that we're trying to maintain, and we want it to somehow take advantage of the new hardware. And part of the problem is just the whole paradigm in Rosetta is based around samples, where each sample is one structure in, a series of operations you perform on the structure, and one structure out, as well as some data from those operations. And then you do another sample that's entirely independent. This is fairly amenable to distributed computing, to lots of CPUs working independently on a problem, but it's not very amenable to GPU computing. What we'd like for GPU computing is a whole batch of structures in, a series of operations that you perform together on each batch, and then a batch of results out. And that would require completely re-architecting the software. Another limitation is we use a single data structure for everything we want to do. We've got this structure called a pose that represents structural information. And this limits our accuracy, our generality, and our efficiency. If I want to optimize sidechain rotamers, I use the packer, which operates on residues, which are things within a pose. If I want to relax the structure, I use the minimizer that operates on the data structures that are within a pose. If I want to sample backbone conformations, I use backbone samplers that operate on the data structures within a pose. The ideal data structure for each of these tasks might be different. And in fact, you might come up with new algorithms that require new data structures, or you might come up with new hardware like GPUs that want new data structures like vectorized data. So what we really want in scientific software is we've got some default data structure. You need some sort of object, and this can be something more like what we're familiar with in object-oriented programming that is very intuitive, that stores all our data. And then you want to do something expensive. And so what you should do is spend a millisecond converting your data to a new representation suitable for that particular task, pass that data representation to an engine that'll do that particular thing that's heavily optimized for that particular data structure and will run for a few seconds. Spend another millisecond converting the solution that you get out of that engine back to your default data structure, and then continue on. And having my ideal software would be set up to make that easy. And the other problem with Rosetta is it's a monolith. This is the organization of the Rosetta libraries. We have our numeric libraries underneath our core libraries. Core libraries define some basic concepts like energies and poses and so forth. Then we have all these protocol layers that go from very general to very specific. Up here somewhere we have RNA modeling techniques and peptide modeling techniques and DNA modeling techniques and things that I don't even know about, antibody loop modeling, whatevers. And this because everything has been kept in one giant repository, which is now about 3 million lines of code, and because everything has been made available to the Python layer and to PyRosetta scripts through PyBind 11, this has created all sorts of problems. So one problem is someone has a good scientific idea. They have an idea for a new energy term to add to our energy function. And they say, okay, I want to try it out, but I have to implement it down here in the core because that concept has to be defined at a lower level than all of the protocols that are going to depend on it. And this is what a lot of the scientific advancement is likely to be. Not just I have an idea for a totally new protocol, but I have an idea for making our existing protocols better with some new ingredient. And then a beginning developer says, wait, I'm a scientist, I'm not a software engineer. I don't want to have to touch the core of this software that thousands of people are using and risk breaking something. And so that idea just doesn't really get tested out. And there isn't a lot of energy function development in the Rosetta community, partly for this reason. Another problem is there are bugs in the software. It's 3 million lines of code. There's stuff to fix. So great idea. Let's fix a bug that we found in the core. Well, unfortunately, everything is allowed to see that function interface that I'm now changing. So I make a change there, and now I've got all sorts of function calls up here that are broken. Fortunately, that's a compiler. So it's a big monolithic code base. I've broken 50 places where it compiles. I can spend the next week just tracking them all down and fixing them all. I've done this many times. You do that, and then you run tests and you find more things you've broken and you fix all of those, and that's fine. Except I said that we bind absolutely everything with Python bindings as well. So I've broken any number of Python scripts as well, and I don't know about that. They're out in the community somewhere. So that's a problem. And finally, the open source problem. Science is all about building on good ideas. So let's say I'm developing some other scientific software package. There's something I want to do that Rosetta already does well. I don't want to reinvent the wheel. Well, I should just incorporate Rosetta into my other package and use Rosetta for that part of the thing I'm trying to do, right? Rosetta doesn't have an open source license. I can't do that. And it also doesn't have an API. I could, even if I could do it from a licensing perspective, if I link something else against Rosetta and the Rosetta API changes, then I've broken whatever depends on it. So all of this has been something that we've been beating our head against more and more. And in the last 15 minutes, I'm going to tell you about Masala, which is something that I intend to be a free and open source successor to Rosetta that addresses these problems. I call it masala because I wanted to take the best ideas and just be a mixture of all of them. Masala in Indian cooking is a mixture of spices. And I also want it to be not only something that you can use as a standalone operation, a standalone set of applications, but also as a library that you can throw into something else. So masala is something you throw into all sorts of other dishes. And I wanted to have a versatile plugin architecture that makes it easy for biologists to extend it just by writing one CC file and one HH file and having the rest of Masala know how to work with that thing, and that could be compiled separately. So some of the ideas in Masala we're borrowing from Rosetta and making better. In Rosetta, I implemented a thread pool. In Masala, we're building everything from the ground up to be thread safe and to work with shared memory parallelism. We also want it to be GPU compatible from the beginning, although I haven't done as much on the GPU side. One problem that we have in a lot of scientific software is you have big modules that solve a big problem that call smaller modules that solve smaller problems that call smaller modules still, and you want those pieces to be interchangeable. And both the small modules and the big modules might want to parallelize their work. Now, if you have a big module that says, I want to launch 256 threads to solve this problem, and each of those threads is calling a smaller module, and the smaller module is saying, I want to launch 256 threads to solve this problem, now you've launched 16,000 threads and you've crashed your node, and SCC is yelling at you, and so on and so forth. So, and as far as I could tell, I didn't see a really good way of dealing with this with any of the software solutions out there. I tried to figure out how to do this with OpenMP and so forth. In the end, I ended up spinning my own thread pool manager, which maintains a thread pool. You can pass work to this thread pool. If there are available threads, it'll assign the work to threads. But if the threads are already doing other work, it'll just do the work in the thread that's asking for the work. So you're guaranteed at least one thread, the calling thread, and up to the number of threads that you're requesting.
Can I ask if you've split that off, or does it have will it live as its own repo with maybe a much simpler use example?
That's my final slide. I have not split it off yet, but that's the question that I have. Is this useful for other scientific software?
Just the thread manager I'm talking about.
Yes.
Right.
Yeah.
When it comes to first touch principles, though. So first touch, say I have a STD vector, and I do an STD vector without threads, and I don't do AMP parallel 4, and I initialize that vector. Okay, and then now I do an AMP parallel 4 and I act on that vector. I'm going to have less, my memory is not going to be SIMD optimized because when I initialized it, I didn't do an AMP parallel 4 when I was initializing.
Right, that can be a problem. Let's talk later. Just to show you here, testing this out on the Rome nodes. This is trying to do parallel Monte Carlo trajectories for optimizing rotamers in Masala. And we get pretty much linear performance up to about 90 or 100 cores, which is more or less about the best you can do on the Rome nodes anyway. I've never seen a benchmark on the Rome nodes that is linear up to 128. So, that's pretty good. Maybe it could be made a little bit better. But now, we also want this to be very modular with well-defined APIs. So the core of Masala is actually a pretty small library that defines abstract-based classes and managers only. outside software is not allowed linking the core. It can't see any of the functions in core. Instead, we have a layer, an API layer, which outside code is allowed to see. And this is Masala. On top of this, you can write plugins that can see the API layers and can do whatever you want, the particular application-specific stuff. A user can use any combination of these plugins. If I'm not working with RNA, I don't want to have to download and compile the RNA plugin. And each of the plugins has its own API layer that outside software can see. And so if you have a user interface like PyMasala or a GUI, I'm calling Garam Masala, the GUI can see the API layers and can auto-generate interfaces from these API layers. Okay, this sounds great. This sounds also very complicated for a beginning programmer to implement. How do you make this accessible to a beginner program? So a plugin developer, my biologist who wants to write something, is responsible for only one thing. If they make their plugin library and they have a class in their plugin library that they want to have an accessible API to, all they have to do is write a single function that defines the API for that class. It returns an object describing the API. The build system handles everything else. Everything else is automated. It builds the handwritten code that the programmer has written. It calls the API definition functions and generates a JSON description of the API for that plugin. And from the JSON description, it writes the C++ code for the API layer. A human never has to touch that. And then it compiles the API layer. And this is actually working really well now, and it makes it much easier to write APIs. Something that links Masala just has to interrogate the Masala plugin manager at runtime to find out the available plugins, request a particular plugin for a particular task, and then query that plugin class for its API description to figure out how to use it. The test system gets the benefit of not only being able to write unit and integration tests, but also you have this JSON description of the API that you can easily write a regression test for. Have I broken the API? And user interfaces can also query the API for the description of what are the knobs you can twiddle in any given class, and use that to generate user controls automatically and documentation automatically. I'll go through this very quickly. If you have a handwritten class with private inner workings, public functions that you want to be part of the API, and public functions that you do not want to be part of the API, but you want to be available to other things within the library, these you've described in your API definition function. And the thing that gets auto-generated is a container that just has functions that call the inner class functions. And we might as well put the thread safety in the container. So this also helps beginning developers. You don't have to write thread safe code. Your container is thread safe. The library needs only have one extern function. This basically just registers the library with the plugin manager and includes some information about the version of Masala that it expects. And it'll throw an informative error message if you try to use your plugin with the wrong version of Masala. This also gets auto-generated. Special type of representation. I've only got a couple minutes left, so I'm going to wrap up very quickly. Engines and data representations. Engines are things for doing a particular expensive task. Data representations are the things that engines operate on. We have an engine manager. We have a data representation manager. Client code can query the engine manager for an engine that meets a set of criteria. So the criteria can be related to hardware. It can be related to the desired algorithm, Monte Carlo versus branch and bound or something like that. It can be related to desired properties, something for sparse matrices, something that's low memory, or it can be an engine that works with a desired data representation. It'll get back engine creators, and it can create an engine and use the engine. And similarly for data representations. You can query the data representation for a manager for a data representation compatible with a set of properties. You get back your data representation and you run with it. A test case of this was implementing quantum computing methods in Masala. And because I've got very little time left, I will just say that the packing problem is NP hard. It maps to quantum computers. We have on both the IonQ gate-based quantum computer and on the D-Wave quantum annealer designed peptides. This is a peptide that we designed on the quantum annealer, made in the wet lab, solved the crystal structure of, but all of this was done with one-off Python scripts. We now want this in C++ code so that we can use it in our existing pipelines. And there are also many, many ways we can map the problem to quantum annealers and quantum computers, and there are many other biological problems that can map to this. So Tristan's project over the summer, he was a very bright intern who did not have a lot of software engineering background, but had a lot of background in quantum computing and in biochemistry. His job was to implement all of the code that would allow Masala to talk to quantum computers and encode problems for the quantum computer and make it all compatible with Rosetta. And I will very briefly jump to the punchline and say, now in Rosetta, you can pass Rosetta a flag saying, here's my Masala plugin library. It will auto-generate an interface for the modules that are available in that library at runtime, and even auto-generate user-facing documentation for how to use those modules. And all of this was done by a beginning software engineer. So all of the parts that are hard have been automated. And with that, I'm just going to finish off and say, some of these things might be useful for other software engineering projects, particularly here at Flatiron. Should we make a starting software engineering kit so that we can start projects and not have to write a thread manager from scratch, or an API container system or a plugin system from scratch? And with that, I'm happy to take questions in the last 3 minutes and 30 seconds.
Okay, thanks for a great talk. Questions? Yes.
You have the build system up again here. Can you just say a little more of that? Is that something you managed to cram into CMake, or is it something bespoke? Or
it's a combination of CMake and a few Python scripts. And it probably could be a little bit better. My Python foo and CMake foo are not as good as my C++ foo. Yeah, it's working better than I thought it would. And it's, so yeah, if others would like to contribute to it and make it better still, I would welcome that. But yeah, it's a combination of CMake and Python. Up is good.
Okay, here we go. Sorry. So I want to ask regarding the slide on the validation of peptide design.
Yes.
I missed what Rosetta energy is.
Oh, yeah, sorry. That's just, so Rosetta has a force field for computing conformational energies. We're just putting the peptide into each conformation that we're sampling, relaxing the peptide in that force field, which is gradient descent minimization using the force field, and then computing the final energy again with the force field. I should mention, now we can also do that with quantum chemistry. And that's actually one thing that the quantum chemistry seems to really be excelling at, because peptides are small enough systems, and yeah, and one thing that's nice is it gives us a lot of samples where we've got calculations done both with quantum chemistry and with our force field, which also gives us a way of calibrating our force field to make the force field better. But yeah, usually when we're calculating energies, we're using a force field, and yeah, and it's a sum of a Leonard-Jones potential and a hydrogen bonding potential and a Coulombic potential, and so on and so forth.
Thank you.
Other questions? Okay, I could ask one. Not about software, but about the science. So what about kind of DFT plus machine learning force field? So instead of doing DFT on the fly, you do many DFT calculations to learn some force field, and then you use those force fields. What's the status of that?
This is something we're super interested in. So there are kind of two branches there. One is there are people already doing this, but with training sets made from small molecules and material science. So one option is just use one of their ML models. The other is now that we can do lots and lots of protein conformational sampling and lots of DFT calculations, let's make our own training set and then train our own model, which is something we're interested in. We have not done that yet. But yeah, I think it could be very, very useful because if we think of QM calculations as expensive but accurate, and then force fields as inexpensive but fast, fast but inaccurate, a neural net is actually slower to evaluate than a force field, but much faster than a QM calculation. And it will be, if you train it on QM, it'll be less accurate than the QM, but potentially more accurate than the force field. So it could be this nice middle ground when you want something that, takes a little bit longer to evaluate, but gives you a little more accuracy.
And then you do full DFT for a smaller number of.
Yeah. And again, I showed you that progression from low cost per sample and lots of samples to high cost per sample and very few samples, throwing away possibilities along the way. You could imagine use a force field a lot at the beginning, use a neural net in the middle, and use full DFT at the end. Yeah.
I see. Very interesting. Okay, so maybe we should leave it at that. Thanks again.